In this problem, you are asked to find the pressure on a reflecting and an absorbing surface from sunlight with a given intensity of 1.3 kilowatts per meter squared, which is the intensity of sunlight at the surface of the Earth. So let's go ahead and do that. What we're going to use is we're going to use the fact that that intensity is the magnitude of the Poynting vector. And furthermore, we're going to use that I can get a momentum density as 1 over c squared times the Poynting vector. We know that as well. So by dividing this number by c squared, I can get the momentum density in the sunlight. And yeah, so that's that. That's not too much. After that, we want to know the change in momentum as sunlight drops across. And so the change in momentum over the change in time, right? This is going to give us essentially the force per unit area, or the pressure of this change in momentum over change in time. Where here we're going to really talk about momentum density. When we do that, that's going to be simply c times the change in the momentum density. And so now we have to talk about these two problems. For a reflector, we start with momentum going that way and then coming up that way, so the change in the momentum density is going to be twice the scale of the momentum density that we have up here. And so this is 2 over c squared times that s. Plug in some numbers for us, and then the pressure that we're going to feel is our 1.32 times 1.3 kilowatts, so times 10 to the third kilogram meter squared per second squared per, so that's kilowatts per meter squared, so per second cubed per meter squared. That's a kilowatt per meter squared, divided by 3 times 10 to the 8th meters per second. That is the speed of light. So the pressure here is going to come, when I plug in these numbers and round to 2 decimal places, this comes to right around 8.2 times 10 to the negative 6, and this is going to be in pascals. For an absorber, our initial momentum is that way, our final momentum is nothing, and so our delta change in momentum is going to simply be s over c squared, which is going to give us half the pressure, right? So the pressure is going to be 4.1 times 10 to the negative 6 pascals. The final thing we're asked to do is to compare this to atmospheric pressure, and I generally don't remember atmospheric pressure. I think atmospheric pressure is like 10 to the 5th pascals or something like that. So I'm going to pull out my handy dandy phone and look up, use Google and do atmospheric pressure, and standard atmosphere is 1.013 times 10 to the 5th, so around 1 times 10 to the 5th pascals. And so this is 11 or maybe only 10 orders of magnitude smaller than atmospheric pressure, but it's much, much smaller than atmospheric pressure.